A Lewis structure is a two-dimensional representation of a molecule that shows the bonds, as oftentimes lines, and then lone pairs, which are unbonded electrons, as the dots around atoms. So jumping right into an example, you'll see that Lewis structures are pretty simple. First, count your number of valence electrons in this molecule. If we're going to draw nitrogen trifluoride, then we need to know that nitrogen has 5 valence electrons, and that fluorine has 7, but there are 3 fluorines, so it will be 5 plus 3 times 7. And that gives me a total number of electrons of 26. I call this my electron bank. Whether they are lines or dots, the total number of electrons I have to use is 26, because valence electrons are the only electrons that matter. The next step is to identify your central atom. The central atom will usually be the first atom, unless that first atom is hydrogen. It takes some practice and experience to determine what the central atom is. Sometimes you will be told, and sometimes you'll figure out that it doesn't make sense for something to be the central atom. In this case, nitrogen is the central atom. When I draw my Lewis structures, I want to make sure that my central atom's in the middle, and then my non-central atoms, my 3 fluorines, are around the edge. It doesn't really matter where they go, but it makes the most sense to spread them out. You will learn more about where they go as you refine these Lewis structures. I call what I have right now the naked atoms, which are basically the atoms in a spatial arrangement that makes sense, such as a central atom with 3 outside atoms, but there are no electrons in the structure yet. The first step is to think about what you have in your bank, this is your electron bank, and then bond everything just once. What that means is connect your inside atom to the outside atoms, such as this. Don't bond your outside atoms to each other. Once you bond everything just once, subtract that number of bonds times 2 from your valence number, because each line that you just drew represents 2 electrons. So I just drew 3 lines, and those 3 lines, those 3 bonds, represent 6 electrons used from my bank. So minus 6. And this is just me keeping a tally. I've used 6 of my 26, that leaves me with 20. That means I have 20 valence electrons left to use. I'm going to use these valence electrons by first spreading them out around the edge. And that will be shown in blue. So these 20 valence electrons get spread around all the outside atoms so that they have 8 valence electrons, except if that outside atom is hydrogen, in which case it should only have 2. So these fluorines, which are not hydrogens, should have 8 valence electrons, and each one already has 2 according to the bond. So if I'm looking at the top left fluorine, I have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons for that fluorine. But of course I have just used 6 of my 20. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Once you run out of room on those outside atoms, and you still have some remaining, so 20 minus 18 equals 2, then where do those 2 remaining valence electrons go? You have no more room on the outside. When you run out of space on the outside atoms and you have remaining valence electrons, then you put them on the inside atom. That would be 19, 20. I've just used all of them, which means I have no more valence electrons remaining, which is good. This would be the structure for nitrogen trifluoride. You could redraw this to make it seem more spatial to you, but this is a two-dimensional representation. Let's draw dichloromethane. The central atom will be this carbon here. So putting carbon in the middle, then the most logical way to spread out the 2 H's and the 2 Cl's will be around the edges, such as this. Now first, I'm going to count up my valence electrons. My valence electron count will be 20 valence electrons to use. That is my electron bank. Now I've already drawn my naked atoms, which means that I can move on to the step where I simply bond everything once. So I have 20 valence electrons in my electron bank, and I've just used 1, 2, 3, 4, 5, 6, 7, 8. Minus 8 leaves me with 12 valence electrons right now. What do I do with those 12 electrons after I've bonded everything once? Multiple possibilities can happen, but the first one that makes the most sense all the time is to take those 12 and spread them out around those outside atoms. But it's important to know what those outside atoms are. So if I code this to be orange, then these 12 valence electrons will get spread around those outside atoms until there is no more room. Hydrogen can only have 2 valence electrons, maximum, which means that hydrogen will never have lone pairs or dots around the symbol as an outside atom. So the bond that you see connecting the hydrogen to the carbon is all that hydrogen can have. So you move on to where chlorine is. Chlorine can have up to 8 valence electrons when it's an outside atom. It already has 2 in the bonds, so 1, 2, 3, 4, 5, 6 of my bank, and then another 6. 1, 2, 3, 4, 5, 6. That leaves me with no more valence electrons left, which is always the goal. Now let's pause for a second and think about why I've spread them out this way. This chlorine has 8 valence electrons, 2 in the bond, and 3 pairs that are not bonded. And the same is true for this. Looking at our complete structure of dichloromethane, we are done. This would be the Lewis structure for dichloromethane. In drawing formaldehyde, we recognize that our central atom is carbon. Spreading the 2 H's and the O, logically, you might put them in positions such as this. Now, counting up your valence electrons, which can be your first or your second step, will come up to be 4 plus 2 times 1 plus 6, giving us an electron bank of 12 valence electrons. Of those 12 valence electrons, I'm going to bond everything just once. This uses 1, 2, 3, 4, 5, 6 of my valence electrons. So 12 minus 6 equals 6 valence electrons remaining. What you should do first when you have those valence electrons that remain after bonding is spread them out as much as you possibly can. Those 2 hydrogens can't take any more, but oxygen needs 8, and right now it has 2, which are being shared with the carbon. So you will have 1, 2, 3, 4, 5, 6. You've spread out all of your valence electrons, which gives you 0 valence electrons remaining, which is the goal. But there is one small problem. If you zoom in on the molecule, it's easy to see that carbon only has 6 valence electrons, all of which are being shared. Carbon, like most elements, would have 8 when it's most stable. Therefore, you're going to have to make a double bond. This is an important way to understand why redrawing is important. If you use pencil, then you can just erase and add the double bond in until you're proficient at this, and then you can see it coming early. Whenever you have a central atom that is electron deficient, one of your outside atoms, in this case the oxygen, has to share in. What I mean by that is this hydrogen cannot form a double bond with carbon. Neither hydrogen can. However, oxygen, and if you want to think of it as kind of like oxygen being generous, oxygen will take one of its lone pair and create a double bond between the oxygen and the carbon. When oxygen forms this double bond with the carbon, it creates something called a carbonyl. When oxygen shares one of its lone pairs with that carbon, it is not losing valence electrons, it is just sharing them. This is what it would look like. As you can see now, oxygen retains 8 valence electrons. Carbon now has 8 valence electrons, and the hydrogens have 2 valence electrons each, which is what they prefer to have for stability's sake. If you examine each of the atoms, you have 8 for the oxygen, 8 for the carbon, and then 2 for the hydrogen, sorry. In general, forming a double or triple bond between the central atom and one of the outside atoms or more is typically only necessary when the central atom is electron deficient after you've already spread out all of the valence electrons around the edge. To draw hydrogen cyanide, count your valence electrons. 1 plus 4 plus 5. That totals 10. You will want to have 10, not 10, you should want to have an even number of valence electrons. So 10 valence electrons is what I'm going to use in my electron bank. To draw that hydrogen cyanide molecule, you want to remember that the first atom is the central atom unless the first atom is hydrogen. In this case, the central atom is a carbon. So the molecule will start to look in the naked structure as HCN with spaces between. Now, of my 10 valence electrons, remember to bond once to start. 1, 2, 3, 4 have just been used. So subtracting 4, and that leaves me with 6 valence electrons to remain in the structure. Take those 6 valence electrons and spread them around the edge. Those 6 valence electrons spread around the edge, which means spread around hydrogen and nitrogen, informs me that I can't use hydrogen to do this. We know that hydrogen can pretty much just have one single bond ever. So now I've got to look to the nitrogen side. Nitrogen has 2, 8 is preferred, so 1, 2, 3, 4, 5, 6 gives me no more valence electrons, which is always what I want. I've run out of valence electrons, but this structure has a problem. If you look at that central atom, just like the last example, it is electron deficient. It only has 4 electrons around it, and it needs 8. Hydrogen is incapable of forming a double or triple bond, but nitrogen can do both. So let's try just one sharing set. If nitrogen, if you were to pretend like these are people, looks at the carbon and thinks to itself, wow, I'm going to share one electron pair with you to start, and let's see how that goes, because you look like you're electron deficient. When nitrogen does that the first time, it gives us this structure. Nitrogen now still retains its 8 valence electrons, but carbon went from 4 to 6, which is unfortunately still not enough. Nitrogen looks at carbon again and thinks, okay, I will share one more pair with you, and let's see if that works. When nitrogen shares one more pair with the carbon, then what happens is that carbon finally has 8 valence electrons. Nitrogen has retained 8, it's just sharing 3 pairs of valence electrons. And everybody has the set that it prefers for stability's sake. Now some teachers will say, well, really disagree with the idea of personifying atoms and molecules, but it's an important way that some people really can help think about what's going on here. So, hydrogen has 2, carbon has 8, and nitrogen has 8. On an exam and in real life, you never want to say an atom is happy or want or prefers because atoms don't have feelings, but I think that it's one of the ways that we can help understand and teach some of these basic concepts. Of course, it all refers back to stability. To draw sulfur trioxide, count your valence, which would be 24, and if 24 valence electrons are in my electron bank, and I put my central atom with my 3 outside atoms, then I'm nearly complete with a little bit of extra work to go. Of course, I need to bond everything once. 1, 2, 3, 4, 5, 6 electrons have just been used from my electron bank, leaving me with 18 remaining. If I have 18 valence electrons remaining, those go around the outside first, and they should be spread in this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have run out, and that's good. Once you run out of valence electrons, then you should look at the central atom and see if it has met its octet. The central atom, the sulfur, has 6 valence electrons, so it is electron deficient. To redraw it, you should pick any one of those oxygens and recognize that that oxygen must form a double bond, or share in, with that central atom. When you do this, remember to remove the lone pair that were once where we decided to share in. Each of these oxygens is equivalent. One of the things that you can do just to make it more conventionally attractive as far as the formula goes is if you look at this top oxygen, there are 2 lone pair that are positioned in a way that could be best drawn this way. 1, 2, 3, 4. I just moved them around to create more of a trigonal geometry around that oxygen. And this would be your complete structure for sulfur trioxide. Both S and O have 6 valence electrons each, which means that sulfur dioxide has 18 valence electrons in total. With my central atom being the sulfur, I can position my oxygens around that sulfur like this. I bond them once, which leaves me with, since each bond represents 2 electrons, I have to subtract 4 electrons from my bank, giving me 14 valence electrons remaining to use. Remember that after you've bonded everything once, spread them around the edge, and then work with any possibilities that may come up. Those remaining 14 are going to go 1, 2, 3, 4, 5, 6, go to the other side, 7, 8, 9, 10, 11, 12. This is one of our situations we've talked about already. I have no more space on the outside to put those valence electrons, so I have to put them on the inside now, which gives me my 14. And there's still an issue. So the first situation is I ran out of space around those outside atoms, so I had to put the remaining valence electrons on the inside. Now you look on the inside atom and determine if it's electron deficient or not. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons, and 8 is the preferred for its octet rule. When that central atom is electron deficient, pick an outside atom's lone pair and share in as many times as you need to. I'm just going to pick this right oxygen for no reason, and the right oxygen is going to share in 1 pair. When it does this, then this is the first resulting structure. If you decided to put that double bond on the other side, then that would be just fine. This is one possible structure. A lot of molecules, as you may learn in your class, can come up in one of multiple resonance structures. Atoms don't have brains or feelings or preferences, so the left structure and the right structure are both equally valid, and in reality, the sulfur dioxide molecule exists between these two structures in something called a resonance structure. It's hard to draw on paper, but you can use this arrow to represent the two possibilities or more possibilities between an atom and its Lewis forms. Our last example, oxygen difluoride, has a total of, let's see, there would be 6 plus 2 times 7, that would be 20 valence electrons. With oxygen in the middle and the fluorines around the outside, I can bond them once like this. 1, 2, 3, 4 have just been used of my 20 in my electron bank. Minus 4, and that gives me 16 valence electrons remaining. Those 16 valence electrons that remain are going to be spread around the edge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember, if you run out of space around the edge, then the remaining have to go on the inside. 13, 14, 15, 16. That leaves me with no more valence electrons remaining, and this would be your Lewis structure. As you work toward understanding Vesper theory, which is the three-dimensional shape of molecules, you will see that this molecule has 4 electron regions around that central atom. 1, 2, 3, 4. This central atom has 4 electron regions that are composed of 2 bonding areas, that's where the 2 real atoms are connected, here, and 2 lone pair, which are here and here. That would give us a shape that we call bent for the molecular geometry, and the electron region geometry would be tetrahedral. If you don't know anything about that, then don't worry about it, but if you're watching this video to review because you've already been exposed to three-dimensional Vesper theory, then that might help you make a connection between the two-dimensional nature of molecules, such as Lewis structures, and the three-dimensional nature in Vesper theory, valence shell electron pair repulsion.